This video will cover section 5.2, verifying trigonometric identities. The objective for the section, of course, it will be to verify trigonometric identities. So what I have written down here, please copy it on your notes. It is an example of an identity. So if we look at the left side by itself, that is called an expression. And the right side is another expression. So I'm going to refer to them as the left and right side. So how do we verify that this is true? And I don't want you to be confused with solving for x or anything like that. I know we do have an equal sign, so yes, it is an equation, but we're going further into that equation. So when we call an equation an identity, we are saying that both sides are equal to each other. And so to verify this, what we're going to do is to turn one side into the other. So for that reason, we can only choose one side to work on. And it's actually better if you go from a more complex side and try to make it look like the simple one. So we're going to start with the left side. And to verify that this is true for all values of x, we're going to make it look like the right side. So it's going to be at the end cosecant of x. So what we could do first is to write everything in terms of sine and cosine. And so for cotangent x, by the quotient identity, that is equal to cosine x over sine x. Cosine x, I'm just gonna write it down here. And I'm not going to do anything to the right side. Okay, now what I'm going to do is multiply the fractions that I have here. And so I will have sine x plus numerator times numerator. So cosine x times cosine x is going to give me cosine square x. And on the bottom, I'm going to have sine x. I'm doing nothing to the right side. Now, what I have here is two fractions with a different denominator. And for me to add them, I need to have the same denominator. And so between 1 and sine x, the common denominator will be the product of 1 times sine x. And so for that, to make this one turn into sine x, we have to multiply the top and bottom by sine x. Again, why do I do that? Because I want both fractions to have the same denominator. So the second fraction already has that denominator. I don't need to do anything to it. Now to the first fraction, we are going to multiply it because we are trying to get sine x on the bottom. So by multiplying by sine x over sine x, what I'm doing here is just multiplying by 1. So if I multiply numerator times numerator, I will get sine x on top, and then sine x times 1, I will get also sine x. So now that they have the same denominator, I can go ahead and add them. And actually, I just realized that I'm missing sine x times sine x should be sine square x. So now they have the same denominator, so I can put them both under one fraction. We have sine square x plus cosine square x. And so by the Pythagorean identity, we know that this is equal to 1. So we have 1 over sine x. And by the reciprocal identity, we know that sine x is equal to cosecant x. And that's what we were trying to prove or to verify, that the expression that we started with at the beginning um, on the left turned into what we have on the right. So now once we achieve that, then we could say that the trigonometric identity has been verified. In this section, you will study techniques for verifying trigonometric identities, and remember that a conditional equation is an equation that it is true for all, for only some of the values. So conditional is only for some of the values in its domain. And that would be, for example, the equation sine x is equal to 0. And it is only true for multiples of pi if you consider this n here an integer. And just to refresh your mind of what I'm talking about, that's our xy axis. And so if we were to have a unit circle here and to solve for values of x, that where sine will be equal to 0, and that will occur, well, actually this will be the unit circle, so that will occur whenever the angle measure, or in this case x, um, is equal to 0 or to pi, because in the unit circle the coordinates of those points will be 1 comma 0, and here -1 comma 0. And so we know that if we complete one full rotation, then we will have 2 pi, and this could be 3 pi. A full rotation plus pi is 3 pi, and then 2 rotations will be 4 pi, and so on. And so that's why we said that for all multiples of pi. And so that is when the conditional equation is true. And so this is the conditional equation. Now, the one that we did at the beginning, that is not a conditional equation, that is an identity, because we were saying that it will be true for all values, not only for certain multiples of pi. So here we have another example of an identity. And so on the other hand, an equation that is true for all real values in the domain of the variable is what we called an identity, like the one we did at the beginning of the video. So this should be familiar to you. This is actually the Pythagorean identity, and we're going to use it a lot. In fact, every time we find it, we will be happy because we will be able to replace that expression with the number 1. But another use of it is to solve for sine square x, like we did here, and we did a little bit of that in the previous section. Or we could also solve for cosine square x, and it will be something like that. And so if we're using an identity, what we're saying is that this is true for all real numbers of x, not only for certain x values or certain multiples of pi. Although there are similarities, verifying a trigonometric equation is an identity is quite different from solving an equation. And as I mentioned before, we only work on one side. And when you work on solving an equation, you usually, or yeah, you do work on both sides. So with an identity, only one side. There is no well-defined set of rules to follow in verifying trigonometric identities, and it is best to learn the process by practicing. So, not to scare you, but Sometimes you might get stuck. Remember to use the tutoring services, and or you can send me a question while you're doing your homework, or you could attend my office hours. That's all I can tell you. But yeah, it could become a little frustrating sometimes. So we're gonna go over the guidelines that are here. You don't need to write them down if you don't want to, but please keep them handy. So number one, you need to work on one side of the equation at a time. Most of the time you will only work on one side and stick to that one side, but there are a few cases where there might be nothing else for you to do to verify the identity, and so you might have to work on the other side, but always one side at a time. Number two, look for opportunities to factor, um, add fractions, or square a binomial or create a monomial denominator. Then number three, look for opportunities to use the fundamental identities. So the ones that we have been working with, such as the Pythagorean identity or the reciprocal identities, the quotient identities. Those are our fundamental ones. Note which functions are in the final expression you want. Sines and cosines pair up well, as do secants and tangents, and also cosecants and cotangents. And those are variations of the Pythagorean identity, actually. Number four, if the preceding guidelines do not help, then try converting all terms to sines and cosines. This is one of the things that I usually start with. Number five, always try something. Even making an attempt that leads to a dead end can provide insight. So, if you do get to that dead end, it's okay. But like we said before, practicing is the only thing that will help you out. Why do you have to learn how to do this? Just to well, it's a very nice skill to have that will help you on calculus and other engineering courses, because you will be able to simplify or to recognize an expression and be able to replace it with another expression. Because if they are an identity, then you could always replace one with the other for all input values, and it will always be true. That's what an identity is. Verifying trigonometric identities is a useful process when you need to convert a trigonometric expression into a form that is more useful algebraically, or imagine something that will be more useful for you to manipulate. So in this case, I wrote down an identity, and you could see the left side. We could see that it is more complex. You have two trigonometric expressions multiplying each other. And on the right side, we only have one expression, which we could consider it a monomial, since it's just one term. And on the left side, we have inside each set of parentheses, we have two terms, so we have two binomials. They just happen to be trigonometric expressions as well. So what we're going to do is verify that it is true. So to do that, we cannot assume that the two sides of the equation are equal. And this is because we are verifying that they're equal. So if we assume, then we don't need to verify anything. So, to the contrary of the way that you solve an equation, you assume they're equal and then you work on both sides um, at the same time. For example, you could add, with equations, you add the same quantity to each side of an equation, or you do cross multiplication when you're solving equations. So, for when you're verifying identities, you cannot use all of those operations. So, This is what we do with equations. You don't do that when you verify identities. Don't add sign of x to both sides, or don't divide by sign of x all across. Don't do things like that. So again, we only work on one side at a time. So what I'm going to do here is refer to the Pythagorean identity, and that one will come in handy a lot. And then I am going to try to make it look like the one that we see here inside the parentheses. So if I leave my cosine square x on the left side, take the positive one from the right to the left, it will be a negative one. And then we will take this positive sine square x to the right side, so it will become negative sine square x. Okay, so what I'm going to do is replace the binomial cosine square x minus 1 with the expression here, negative sine square x. And what I'm going to do is use another variation of the trigonometric Pythagorean identity, and I'm going to replace that one. One of the variations of the Pythagorean identity that we discuss in chapter 4, but also in section 5.1, it is the one that states that 1 plus tangent of square of x is equal to secant square of x. And it is on the first couple of slides, I think, of section 5.1. And so what I'm going to do is replace the binomial here with the monomial secant square of x. Now I'm going to rewrite secant square of x with the reciprocal identity 1 over cosine square x. And then my second monomial or trigonometric expression is just going to stay like that. Okay, now if I multiply those two fractions, numerator times numerator, denominator times denominator, I will get negative. So 1 times negative sine square x, I will get negative sine square x. And then cosine square x times 1 will be cosine square x. And finally, if you recall from the quotient identity, the ratio that we have here is equal to tangent square x. And of course, we cannot forget that we have a negative here. So we do need a negative here. And so once we arrive at that point, or in fact, I should just write it here, because I told you we're just going to continue working on one side. And so that equals negative tangent square of x. And so we just verified another identity. The next identity that we're going to verify, it is written down here. And as you can see, the left side is more complex, so we're going to try to work it out so it looks like the right side. So again, we're going to use the Pythagorean identity, and actually I'm going to use a substitution that we used on the previous problem. In that case, I'm going to go just back for a second. What I'm looking for is the identity that we will use to replace secant with the expression that we see here. Okay, and that one is the one that we use here. And so let's see how we arrive from the main Pythagorean identity to that one. It's just good practice. And so what we're going to do is to divide everything by cosine square x. Here I'm not verifying an identity, I'm just trying to simplify the expression. Well, actually not simplify it, but transform it, all of it, so that I can get a variation of the Pythagorean identity. So we had a 1 and we divide, we say by cosine square of x. So if we do that, the first fraction by the quotient identity, this one is equal to tangent square of x. The second fraction is equal to 1. And the right side here is equal, by the reciprocal identity, is equal to secant square of x. And that is the same that we used before to replace this part here with the, actually not that one, but it was the tangent square of x. We replaced that with secant square x. It came from here. So just so you know, that one came from the main Pythagorean identity, which is here. Okay, so now that we know for sure that secant square of x, we're going to replace it with tangent square x plus 1. And so that is the first step here. And I know I told you to just keep working on one side, so just to follow my own rule, I'm going to do the following. I'm just going to do the substitution on the left side. So instead of secant square of theta, I'm going to write tangent square of theta plus 1. Okay, now let's not forget that we have a negative 1 here, so I still need to write it down. And now from here, if I remove the parentheses, I will have tangent square theta plus 1 minus 1 equals. And positive 1 and negative 1, they're opposites, so they're equal to 0. So now we have tangent square theta equals. And, oh, actually, I forgot to write down the denominator. So I'm going to go back, and this quantity here, I'm going to go ahead and I need to write it down here as well. Okay. Now I'm going to do the subtract the ones. So we will have tangent square theta over secant square theta. So what I'm going to do here is I could always split the fractions that are multiplying, so or they're dividing, but you could also write them as the product of two fractions. A quotient could be written as the product of two factors or fractions in this case. So it's kind of like I'm separating them, but in reality they're still multiplying each other, like that. And so For tangent, what I'm going to do is use the quotient identity, and that will be sine square of theta in fact, I'm just going to write it here. So sine square theta over cosine square theta times 1 over secant square theta. And what we're going to do here is use the reciprocal identity for 1 over secant square theta, and that is going to turn into cosine square theta over 1. So now when we multiply here, we could actually cancel cosine square theta divided by cosine squared theta because they equal to 1. They don't disappear, remember, they equal to 1. So now I just have sine squared theta, and that is equal to the right side, which is sine squared theta. We're going to do a few more examples because the PowerPoint only had one. I've been adding some, so let's do a few more. We're going to work on the left side, and we're going to try to rewrite that left side as the right side. If we're able to do that, that means the identity is true, and that's how we verify the identity. So I'm going to use the quotient identities first. For tangent, we're going to replace that with sine x over cosine x. For cotangent, quotient identity is cosine x divided by sine x. Okay, and now what we're going to do is add the two fractions. Now remember, we discussed just like fractions with numbers, with integers, if we don't have the same common denominator, we have to have both fractions with the same denominator so that then we will be able to add the top parts, the numerators. So what we need to do here is find a common denominator, and what we will have to use is actually the product of the two denominators that we see there. So that will be cosine x times sine x. And so what we are going to try to do is have both of the fractions with that denominator. So what do we need to do? So we are going to have to multiply the first fraction. It already has this part of the denominator. So what is missing is sine x. So that's what we're going to do here. Multiply by sine x. But whatever we do to the bottom, we have to do it to the top as well. So if we do that and we multiply here, we will get sine square x. And on the bottom, cosine x times sine x is what we already have here. Okay, now let's move on to the fraction on the right side. And you could see that that one already has sine x is here. So what is missing is cosine x. So we're going to multiply the fraction by cosine x divided by cosine x, like that. So if we multiply here, cosine x times cosine x, that will be cosine square x. And on the bottom, we have this part right here. Okay, so if we now put our two fractions together, because they have the same denominator, that's fine. So it will be cosine x sine x, and then we will write sine x sine square x plus cosine square x. Those are coming from here. We're just writing combining the two fractions. And by the Pythagorean identity, the one that is kind of like I told you, a lifesaver, anytime you see it, you're allowed to replace that by the number 1 because that's what the Pythagorean identity says. So I take this whole expression and just replace it with the number 1. Now that is divided by cosine x times sine x. And I'm going to take a look at where we're trying to get with this identity. And as you can see, it's secant and cosecant. So if you look at where we are right now, we're almost there. We have something with cosine and with sine. And we know that secant and cosine are related by being reciprocals of each other. And so are cosecant and sine. So what I'm going to do is take this fraction, and we did something similar early on the previous problem. We're going to separate that fraction into two factors. And now by the reciprocal identities, we have that 1 over cosine is secant. And 1 over sine is cosecant. And so that is exactly where we were trying to get, what we were trying to verify, I should say. And that's what we have here. On the next example, we're going to work on the left side to verify the identity. So we're going to manipulate the terms on the left so they look like the expression on the right side of the inequality, of the equal sign. Okay, so again, we're going to do something with fractions. We have two different denominators. And so the common denominator is actually going to be the product of one times the other. So you could already imagine that we're going to be multiplying next. Okay, so first fraction, 1, the denominator is 1 minus sine alpha. That one is already here. So that means that we need to multiply by 1 plus sine alpha. So if we do that here, 1 plus sine alpha, that's another Greek letter, and then here as well, 1 plus sine alpha. And we will get just 1 times that, so we will get 1 plus sine alpha. Okay. Second fraction, we have that denominator originally, 1 plus sine of alpha. And so the part of the denominator that is missing is the product of the other binomial here, which is here. And so that's what we're going to use to multiply here, top and bottom. So 1 minus sine alpha. Top and bottom, because remember, we don't want to change the meaning of the expression. We just want to change the way it looks. So 1 times that is just going to be 1 minus sine alpha. Okay. Now, since we have same denominator, we could combine our terms. And so we're going to write them under one fraction. So we have the term in blue, 1 plus sine alpha coming from here. Then we have this one here. Well, I'm going to finish writing the denominator first. And then let's write this part. Plus 1 minus sine alpha. Okay, so from here, we have 1 plus 1, so that will equal to 2. Positive sine alpha minus sine alpha will cancel out. They equal to 0. And now we have the denominators here. So what I want to do is multiply them. So we have two binomials. So if I multiply 1 times 1, I will get 1. If I multiply 1 times sine alpha, I will get positive sine alpha. And then if I multiply negative sine alpha times 1, I will get negative sine alpha. And then finally, I will multiply negative sine alpha times positive sine alpha. And that will give me negative sine square alpha. Then you could see here clearly the two terms in the middle will cancel each other out because they're opposites. And so now we have 2. And we have 1 minus sine square alpha. And from here, what we could do is use the Pythagorean identity. And the reason I know that is because we're trying to get to something that contains secant. And so if we are working with something that is in terms of sine square, we need to figure out a way to get to cosine square, because cosine square is the reciprocal of secant square. So how do we go from sine square to cosine square? Well, we could use the Pythagorean identity. So we don't want to have sine square, we want to have cosine square. So remember the Pythagorean identity, it goes like this. Actually, and let's just write it down here. So it is sine square. In this case, the variable for the angle is alpha plus cosine square alpha equals 1. And if I want to, if you look at what we have here, is 1 minus sine square alpha. So let's see what happens if I have on the right side 1 minus sine square alpha. So it's like if we take this positive and take it to the right side, so then it will be negative, right? Inverse operations. And then on the right side, we still have the expression here, cosine square of the angle alpha. So based on that, what we're going to do is replace this whole thing just simply with, and let's not forget about the 2 that we have here. So we're going to replace that with cosine square. And now by the reciprocal, this could be seen as 2 times 1 over cosine alpha. So then the reciprocal of this one will give me secant square of the angle alpha. And that is what we were trying to verify.